In section 913, we'll talk about tosylates or toluene sulfonates, which is another way to activate alcohols to make them a good leaving group. So let's get started with what this is. This molecule here is toluene, which is a methylbenzene. A six-membered ring with 3 double bonds around it is benzene. So this group here is a tosyl group, or toluene sulfonyl. And the way it's going to be introduced to our alcohols is through the molecule toluene sulfonyl chloride. Again, here's our halogen. So there's typically been a reason why we have halogens on our molecules, and the reason for halogens usually has been because they make good leaving groups. So if we take an alcohol and react that with toluene sulfonyl chloride, once again, see if you can pause the video and determine what happens in this mechanism before I show you. Like what we've been doing throughout the chapter, you have to figure out who has electrons and who wants them. Sulfur is partial positive. Oxygen, and chlorine are all partial negative. So this is who wants electrons, is sulfur. Who has them is our alcohol then. So the electron pair comes in from the oxygen from alcohol into sulfur, and the chloride leaves to make an intermediate. Okay, so our intermediate there is our tosylate. You can see now how you have the toluene, the sulfur with 2 double bonded oxygens, and the single bonded oxygen, like right here in the tosyl group. And now this is going to be a good leaving group, because the leaving group is this tosyl anion, which is the conjugate base of toluene sulfonic acid. And toluene sulfonic acid is a very strong acid with a pKa of about -7. And if you think about why, you look here, this is very similar to what you see in the conjugate base of sulfuric acid, where you have the negative charges can be shared across 3 different oxygens. It's going to be true here in the toluene sulfonic acid, it's going to be shared across 3 different oxygens. The only difference is that you have this toluene group, or toluene group, up on the top, rather than another OH that you would have in sulfuric acid. It's a very strong acid, so that's going to make that a great leaving group. Now, just like some of the other reactions in this chapter, this is done with pyridine. So I can deprotonate the intermediate. And now I can do a couple different things with this intermediate. I can either add something that's a good nucleophile and pretty small, or I can add something that's a good base and pretty big. And I can either get an SN2 type reaction or I get an E2 type reaction. So let's look at the stereochemical outcome of using a tosylate to do something versus using a conversion to an alkyl halide first. So let's say I have this alcohol. If I react this alcohol with phenyl chloride and 1 equivalent of pyridine, I can get it replaced by chloride. Now, if you think about the mechanism, the chloride is going to come in and push off the activated oxygen group. So my chloride is going to be inverted. So that's going to be an SN2 type step to that mechanism. Well then, if I take that compound and react that with sodium cyanide, Again, the cyanide is going to come in and do backside attack, and it'll get inverted again. So I'll get my original stereochemistry, but have my cyanide. Now, what happens if I want my cyanide, but I want it to have the opposite stereochemistry? Well, we can do that with a tosylate. So if I take my alcohol and treat it with toluene sulfonyl chloride and pyridine, I get my tosylate, which now, if I replace that with cyanide, sodium cyanide, it can come in through backside attack again, displace my tosylate, and now I have the opposite stereochemistry. In this two-step synthesis, we have inversion in the first step and inversion in the second step, which causes us to have retention of the overall stereochemistry. In the second synthesis, we have activation in the first step and then substitution in the second step, so I only get one inversion, which gives me opposite stereochemistry.